Hello everyone, and welcome to today's presentation. I'm excited to have you here. Today, we'll be exploring drainage and sewer design thumb rules, featuring 60 practical examples. Over the next few slides, we'll cover key principles and guidelines that can help streamline your design process. I'm looking forward to sharing insights that are both useful and easy to apply. Let's get started. Let's take a look at the sewage generation rules. First, for domestic sewage per person, we typically estimate around 50 to 60 liters per person per day. This is what we call a thumb rule, giving us a quick estimate. The more precise way is to use the formula Q equals P times Q sub P, where Q is the sewage flow, P is the number of people, and Q sub P is the per person sewage generation rate. For example, if we have a house with 4 people, we multiply 4 by an average of 55 liters, which results in about 220 liters per day. This approach is supported by the IPC 2018, specifically Table 703.1. Moving on to commercial sewage flow, such as in restaurants, the thumb rule suggests about 20 to 30 liters per seat per day. So, for a restaurant with 50 seats, we multiply 50 by an average of 25 liters, giving us roughly 1250 liters per day. The formula here is Q equals N sub seats times Q sub S, where N sub seats is the number of seats and Q sub S is the sewage per seat. This guideline is referenced in UPC 710.1. Finally, for schools, the typical estimate is about 30 liters per student per day. Using the formula Q equals N sub students times Q sub S, if there are 200 students, we multiply 200 by 30 to get 6,000 liters per day. Again, this is supported by IPC 2018, Table 703.1. These rules and formulas are essential because they help us estimate sewage generation accurately based on different user categories, which is critical for designing effective sewage systems. Now let's look at some important rules for estimating peak flow rates in different types of facilities, starting with Rule 4, which applies to commercial establishments. The key concept here is the peak factor, or PF, which in this case is 3. The formula is straightforward. Peak flow, Q peak, equals the average flow, QAVG, multiplied by this peak factor. For example, if a commercial site has an average flow of 1,000 liters per day, then the peak flow would be 3,000 liters per day. This rule is referenced under UPC 71021. Moving on to Rule 5, which targets residential areas. The peak factor for residential use ranges between 2 and 2.5, depending on specific circumstances. The same formula applies. Q peak equals QAVG times the peak factor. So, if a household has an average flow of 220 liters per day, multiplying by 2.5 gives us a peak flow of 550 liters per day. This rule is outlined in the IPC 2018, Section 710.3. Finally, Rule 6 addresses hospitals, which typically have much higher flows. Here, the peak factor is 3.5. Using the same approach, if a hospital's average flow is 18,000 liters per day, multiplying by 3.5 yields a peak flow of 63,000 liters per day. This is referenced under UPC 71032. The key takeaway here is understanding how these peak factors help us estimate maximum flows based on average flows, tailored to different facility types. These rules are essential for designing systems that can handle peak loads efficiently and safely. Let's take a closer look at some of the fundamental rules for pipe sizing, starting with Rule 7, which pertains to the minimum diameter for a water closet, or WC. The thumb rule here is that a single WC typically requires a 100 pipe. For example, if you have one toilet, you should use a 100 pipe to ensure proper flow and avoid clogging. According to the IPC 2018, Section 704.1, this is the standard guideline to follow. Moving on to Rule 8, which covers the minimum diameter for kitchen sinks and similar fixtures. The general recommendation is a pipe diameter of about 50 to 75. For instance, a kitchen sink usually needs a 75 pipe to handle the wastewater efficiently. Again, this aligns with the IPC 2018, Section 704.2. The key idea here is that the pipe size needs to match the expected volume to prevent backups and ensure smooth drainage. Finally, Rule 9 addresses laundry and bath drainage. The minimum diameter here is generally 50 mm. So, if you're connecting a bath and laundry drain, a 50 mm pipe is usually sufficient. According to UPC Section 704.1, this size helps manage the typical flow from these fixtures without issues. Overall, these rules are crucial because they help us ensure proper drainage, prevent clogs, and comply with building codes. Proper pipe sizing is a fundamental part of designing efficient and safe plumbing systems. Let's take a closer look at the pipe slope rules, starting with Rule 10 for 100 pipes. The key idea here is that we have a thumb rule of 1 to 50, which translates to a 2% slope. This means that for every 50 units of length, we need a 1-unit drop in height to ensure proper flow. Using the formula delta equals L multiplied by S, where delta is the height difference, L is the length of the pipe, and S is the slope, we can calculate the needed drop for any run. For example, if we have a 20-meter run, dividing 20 by 50 gives us 0.4 meters of drop. Moving on to Rule 11 for 115 pipes, the thumb rule becomes 1 to 100, which is a 1% slope. Again, using the same formula, if we have a 50-meter run, dividing 50 by 100 results in a 0.5-meter drop. This slope ensures proper drainage without causing issues like turbulence or blockages. Finally, Rule 12 applies to 200 pipes, with a thumb rule of 1 to 150, roughly a 0.67% slope. For a 60-meter run, dividing 60 by 150 gives us a 0.4-meter drop. It's important to note that these rules are also supported by codes, such as the IPC 2018 and UPC 2018, which specify minimum slopes to ensure effective flow and prevent problems. Overall, these rules and formulas are crucial for designing efficient piping systems, ensuring that wastewater flows smoothly with gravity and avoiding future maintenance issues. Let's now look at some key rules regarding pipe capacity, starting with Rule 13, which pertains to pipe flow velocity in residential systems. A good thumb rule here is that the velocity should typically range between 0.6 and 3 meters per second. To understand this better, we use the basic formula V equals Q divided by A, where V is velocity, Q is flow rate, and A is the cross-sectional area of the pipe. For example, if we have a 150 diameter pipe and the flow rate Q is 14 liters per second, the velocity V comes out to about 0.8 meters per second. This is within the recommended range and ensures smooth flow without causing damage or noise. Moving on to Rule 14, which addresses the maximum flow a pipe can handle. Here, the flow rate Q can be calculated by multiplying the cross-sectional area A by the velocity V. Remember, the area A for a circular pipe is pi times the diameter squared over 4. Using the same 150 pipe and a velocity of 0.8 meters per second, we find that the maximum flow Q is approximately 14 liters per second. This helps us ensure the pipe isn't overloaded, maintaining efficiency and safety. Finally, Rule 15 emphasizes the minimum velocity needed to keep the pipe self-cleaning, preventing sediment buildup. The thumb rule here is that the velocity should be at least 0.6 meters per second. For instance, with a 100 pipe flowing at 0.7 meters per second, this is considered safe and effective for self-cleaning purposes. All these rules are supported by codes, such as IPC 2018 and UPC, which provide standardized guidelines to design efficient and reliable piping systems. By understanding and applying these principles, we ensure our plumbing systems function smoothly, last longer, and require less maintenance. Let's take a look at some important manhole rules to keep in mind during construction and maintenance. Starting with Rule 16, which deals with the maximum distance between manholes. A handy thumb rule here is that for pipes with a diameter of 100 to 150 millimeters, the spacing should be around 30 meters. If the pipe diameter increases to 200 millimeters, the spacing can go up to about 50 meters. For example, with a 150 mm pipe, you would typically space the manholes approximately 30 meters apart. This guideline is supported by the IPC Code 710.4, which helps ensure proper access and maintenance. Moving on to Rule 17, which specifies the minimum size of a manhole. The key formula here is that the manhole diameter should be at least 1.2 times the pipe diameter. So, for a 200 mm pipe, the minimum manhole size would be about 1.2 times 200 millimeters, which translates to roughly 240 millimeters in diameter. However, practically, you'd use a manhole size like 900 by 900 millimeters to accommodate maintenance and inspection needs. This rule is outlined in the UPC Code 71041, emphasizing the importance of adequate space for entry and work. Finally, Rule 18 addresses the invert drop in a manhole, which is critical for maintaining proper flow. The invert drop is calculated by subtracting the outlet invert level from the inlet invert level. For example, if the inlet invert is at 1.5 meters and the outlet invert is at 1.3 meters, the drop would be 0.2 meters. This ensures that the flow continues smoothly without undue resistance or backflow. The relevant code here is IPC 71042, which guides us on proper invert level management. Together, these rules help us design manholes that are safe, accessible, and efficient for sewer systems. Let's take a closer look at fixture units and stack design. First, Rule 19 relates to the WC fixture unit. The thumb rule here is that one water closet, or WC, typically equals about 2 to 3 drain fixture units, or DFU. So, for example, if you have one WC, it would be considered roughly 2 DFU. The relevant code for this is IPC 709.1. Moving on to Rule 20, which covers basin fixture units. The thumb rule simplifies this by stating that one basin equals 1 DFU. So, if you have 3 basins, that totals 3 DFU. The code associated with this is UPC 709.2. Finally, Rule 21 deals with selecting the appropriate stack diameter. This calculation is based on the total DFU, which you determine from IPC 710.5. For instance, if your total DFU amounts to 20, then a 100 m stack diameter would be suitable. The specific guideline for this is IPC 710.5. Understanding these rules helps us design plumbing systems that are both efficient and compliant with code, ensuring safe and reliable drainage for any building. Let's take a closer look at grease traps and how we determine their size and capacity. First, Rule 22 focuses on the volume of the grease trap. The formula to calculate this is V equals N times 50 to 100 liters per user. For example, if you have 20 users, you'd multiply 20 by 50, which gives you a capacity of 1,000 liters. This helps ensure the trap is large enough to handle the expected grease load based on the number of users. The relevant code for this rule is IPC 1003.1. Next, Rule 23 deals with the flow retention time, which is how long the grease should stay in the trap to separate properly. A good thumb rule here is a retention time of 30 to 60 minutes. For instance, if the flow rate is 20 liters per minute, dividing 1,000 liters by 20 liters per minute gives a retention time of about 50 minutes. This ensures the grease has enough time to separate before the water exits the trap. The applicable code is UPC 1003.2. Finally, Rule 24 combines these ideas to size the grease trap appropriately. The formula here is V equals Q times, where Q is the flow rate and is the retention time. So, if your flow rate is 20 liters per minute and your retention time is 50 minutes, the volume V would be 1,000 liters, matching our earlier example. This rule is covered under IPC 1003.3. Overall, these rules and formulas help us design grease traps that are effective and compliant with standards, ensuring proper grease management and preventing plumbing issues. Let's now look at some key points regarding roof and stormwater drainage. Starting with Rule 25, which concerns the minimum downpipe diameter. A good thumb rule here is to use a 15 diameter pipe for every 20 square meters of roof area. For example, if you have a 100 square meter roof, you typically need 4 15 pipes to handle the runoff effectively. This is based on the standards outlined in IPC 1103.1, ensuring proper drainage and avoiding blockages. Moving on to Rule 26 about the slope of roof gutters. The general recommendation is a slope between 500 and 1,000. To put that into perspective, if you have a 10-meter long gutter, the height difference, or delta, should be around 0.02 meters, which is about 2 centimeters. This slope helps water flow smoothly toward the downpipes, preventing standing water and potential damage. The guideline for this is found in UPC 1103.2. Finally, Rule 27 covers stormwater pipe sizing. Here, we use the rational method, which is a straightforward formula. Q equals C times I times A. Q is the flow rate, C is the runoff coefficient, I is the rainfall intensity, and A is the area. For example, if you have a 500 square meter catchment area, a rainfall intensity of 15 per hour, and a runoff coefficient of 0.8, then your stormwater flow rate comes out to about 5.56 liters per second. This calculation is based on IPC 1104.1 and helps ensure your drainage system is appropriately sized for various rainfall conditions. Overall, these rules and formulas are essential for designing an effective roof and stormwater drainage system that protects the building and maintains proper water flow. Let's take a closer look at some key sewer trench and bedding rules that are essential for proper installation. Starting with Rule 28, the trench width. A good thumb rule here is to make the trench width equal to the pipe diameter plus 300 millimeters. For example, if you're working with a 200 millimeter pipe, the trench should be about 500 millimeters wide. This ensures enough space for proper bedding and handling. According to the code, IPC 704.3, following this rule helps ensure the stability and ease of installation. Next, we have Rule 29, which covers the bedding type. The thumb rule suggests using sand or gravel bedding that's about 100 to 150 millimeters thick. For instance, if you're installing a 150 millimeter pipe, you'd use approximately 150 millimeters of sand bedding to support it properly. The relevant code here is UPC 70431. Proper bedding is crucial because it provides a stable foundation and helps prevent future pipe movement or damage. Finally, Rule 30 deals with pipe embedment. The key idea is that the pipe should be fully embedded in the bedding material. So, for a 150 millimeter pipe, you'd embed it in about 150 millimeters of sand or suitable bedding material. This is outlined in IPC 70432. Full embedment ensures the pipe is well supported along its entire length, reducing the risk of sagging or shifting. Overall, these rules, trench width, bedding type, and embedment, are designed to promote the durability and functionality of sewer systems. Remember, following these guidelines helps us build safer, more reliable infrastructure. Let's discuss the minimum cover and depth requirements for sewer pipes. Starting with Rule 31 for residential sewers, the thumb rule is generally 600 millimeters. For example, if you have a 100 pipe, the minimum depth should be about 0.6 meters. This is important to prevent damage and ensure proper flow. The relevant code here is IPC 704.4. Moving on to commercial or road sewers, the minimum cover increases to about 900 millimeters, or 0.9 meters. So, if you're laying a 115 pipe under a road, you should aim for at least 0.9 meters of cover. This helps withstand traffic loads and other stresses. The applicable code is UPC 70441. Finally, there's the maximum cover limit, which is generally around 3 meters without requiring special support. For instance, a 200 pipe should not be buried more than 3 meters deep, or it may need additional support. This rule is outlined in IPC 70442. Understanding these cover depths is crucial for designing sewer systems that are both functional and durable, fitting into the overall theme of safe and efficient infrastructure development. Let's dive into pipe material selection. First, we have Rule 34, which focuses on materials for sanitary sewers. The thumb rule here is to use PVC, HDPE, or ductile iron, or DI. For example, when installing building drainage, a 115 PVC pipe is a common choice. This rule is supported by the IPC Code 706.1. Moving on to Rule 35, which covers stormwater sewers. The thumb rule suggests using concrete reinforced concrete pipe, RCP, or HDPE. An example would be a 300 concrete pipe designed for stormwater management. This aligns with the UPC Code 706.2. Finally, Rule 36 addresses materials for high-temperature waste. In this case, cast iron or stainless steel are preferred. For instance, in commercial kitchens, a 100 cast iron pipe is typically used to handle hot waste efficiently. This is governed by IPC Code 706.3. Overall, choosing the right pipe material depends on the specific application and environmental conditions, ensuring durability and compliance with relevant standards. Let's start with the combined sewer flow. The key idea here is that the total flow in a sewer is the sum of sanitary and storm flows. This is captured by Rule 37, which states that the combined flow, Q total, equals the sanitary flow, Q sanitary, plus the storm flow, Q storm. For example, if sanitary flow is 2 liters per second and storm flow is 5 liters per second, then the total flow becomes 7 liters per second. This concept is important because it helps us understand how sewer systems handle varying flows during different conditions. Moving on to Rule 38, which concerns the minimum velocity needed for a sewer to clean itself. The thumb rule here is that the flow velocity should be at least 0.6 meters per second. For instance, if we have a 200 millimeter pipe with a flow rate of 7 liters per second, the velocity would be approximately 0.8 meters per second, which is sufficient for self-cleaning. This rule helps prevent blockages and ensures the sewer remains functional over time. Finally, Rule 39 addresses the maximum flow depth within a sewer. The thumb rule states that the flow depth should not exceed 0.8 times the pipe diameter. So, in a 200 millimeter pipe, the maximum flow depth would be around 160 millimeters. Keeping the flow within this limit helps avoid issues like overflows or excessive pressure. Overall, these rules and formulas are fundamental in designing effective sewer systems that can handle varying conditions safely and efficiently. Let's talk about venting and air admittance in plumbing systems. First, Rule 40 addresses the stack vent diameter. A good thumb rule here is that the vent pipe should be at least 50 millimeters in diameter. For example, if you have a 100 millimeter stack, the vent pipe should be around 50 millimeters. This helps ensure proper airflow and prevents pressure issues, and you can find detailed guidelines in IPC 909.1. Next, Rule 41 focuses on the distance between the vent and the fixture. The rule of thumb is that the horizontal distance should be no more than 6 meters. For instance, if you're venting a toilet, the vent should be within 5 meters of the fixture, ensuring effective venting and avoiding siphoning or trap issues. This is covered in UPC 909.2. Finally, Rule 42 discusses vent termination. The general rule is that vents should extend at least 300 millimeters, or about 0.3 meters, above the roof surface. This height helps prevent gases from entering the building and ensures proper vent function. So, when you're placing a vent pipe, make sure it terminates above the roof by this minimum distance, as specified in IPC 909.3. Together, these rules help us design efficient and code-compliant venting systems that maintain proper airflow and safety in plumbing. Let's now look at some key points about inspection chambers and access points. First, according to Rule 43, for a 100 pipe, the spacing between inspection chambers should be around 30 meters. This is a handy thumb rule to ensure proper access for maintenance and inspection. For example, with a 100 pipe, you should place an inspection chamber roughly every 30 meters. This guideline is supported by IPC Code 710.4. Moving on to Rule 44, which deals with the size of the inspection chamber. The thumb rule here is that the chamber should be at least 600 by 600 millimeters. So, for a 115 pipe, you would typically use a chamber of this size to allow enough space for access and work. This is outlined in UPC Code 71041. Finally, Rule 45 covers drops in the inspection chamber for level changes. The typical acceptable drop height is between 150 and 300 millimeters. For example, if you have a 200 drop within the chamber, that is generally considered acceptable and safe for maintenance purposes. This rule is specified under IPC Code 71042. In summary, these rules help us design inspection chambers that are accessible, functional, and safe, fitting seamlessly into the overall plumbing system. Let's take a look at sewer slope and velocity considerations. First, Rule 46 states that for a 100 pipe, the minimum slope should be about 1 in 50, which means a vertical drop of 0.4 meters over a 20-meter run. Using the thumb rule, we simply divide the length by 50 to find the necessary head loss. For example, in a 20-meter pipe run, the height difference would be 20 divided by 50, giving us 0.4 meters. This rule is supported by the IPC Code 710.1. Moving on to Rule 47, for a larger 115 pipe, the minimum slope is a bit gentler, 1 in 100. So, for a 50-meter run, the head loss would be 50 divided by 100, which equals 0.5 meters. The thumb rule here helps us quickly estimate the slope needed, and this is backed by the UPC Code 710.1. Now, the third key point is about maximum velocity in sewer pipes. To prevent pipe damage, the velocity should generally not exceed 3 meters per second. For instance, if we have a flow rate of 0.03 cubic meters per second in a pipe with a diameter of 0.3 meters, the velocity calculates to approximately 0.85 meters per second, which is well within the safe limit. This guideline is outlined in IPC 710.2. So the main takeaway is that proper slope ensures effective flow, and controlling velocity is crucial to prevent damage and maintain system longevity. These rules and codes help us design efficient and durable sewer systems. Let's talk about emergency overflow and sump pumps. First, Rule 49 states that the emergency overflow capacity should typically be about 1.5 times the design flow. For example, if your design flow is 10 liters per second, the overflow capacity should be around 15 liters per second to ensure it can handle unexpected surges or blockages. This is specified in the IPC under Section 1005.1. Next, regarding sump pump sizing, Rule 50 provides a simple formula. Q equals V divided by T, where Q is the flow rate, V is the volume of water, and T is the time in which you want to pump that volume out. For instance, if you have a sump volume of 5 cubic meters and you want to pump it out in 10 minutes, your flow rate should be 500 liters per minute. This is covered in the UPC under Section 1005.2. Finally, Rule 51 addresses the minimum size for sump pits. The thumb rule here is that for commercial applications, the sump pit should be at least 1 cubic meter in size. As an example, a sump pit measuring approximately 1.2 by 0.8 by 1.1 meters equals about 1.056 cubic meters, which meets the minimum requirement. This guideline can be found in the IPC under Section 1005.3. Overall, these rules help ensure our systems are capable of handling unexpected water flows safely and efficiently, which is crucial in maintaining proper building drainage and preventing flooding. Let's now look at detention and retention tanks, starting with Rule 52, which covers detention tank volume. The key formula here is V equals Q times T. This means the volume of the tank depends on the flow rate and the detention time. For example, if we have a flow rate of 20 liters per second and a detention time of 30 minutes, the required tank volume would be 36 cubic meters. This is essential for ensuring the tank can hold enough water for peak flow conditions. The code associated with this rule is IPC 1105.1. Moving on to Rule 53, which addresses freeboard in the tank. A simple thumb rule is to add about 0.3 meters of freeboard to account for overflow and safety. For instance, if your tank height is 1.8 meters, then the freeboard would be approximately 0.3 meters. This extra space helps prevent spillage during heavy inflows. The relevant code here is UPC 1105.2. Finally, Rule 54 deals with outlet sizing. The basic formula is Q equals A times V, where A is the outlet cross-sectional area and V is the velocity of flow. For example, if you have an outlet area of 0.3 square meters and a flow velocity of 0.2 meters per second, the outlet capacity would be 60 liters per second. Proper sizing is crucial to ensure the outlet can handle the expected flow without causing backups or overflow. The code for this rule is IPC 1105.3. Together, these rules help us design detention and retention tanks that are both effective and safe, aligning with the overall goal of efficient stormwater management. Let's take a look at some key rules for pumping stations. First, Rule 55 focuses on pumping flow. A good thumb rule here is to size your pump at about 1.5 times the peak flow rate. For example, if your peak flow is 10 liters per second, you should aim for a pump capacity of around 15 liters per second. This helps ensure you have enough capacity during high flow conditions. The relevant code for this is IPC 1106.1. Moving on to Rule 56, which is about pump head. The pump head is basically the total energy the pump needs to provide, and it's calculated by summing three components: the static head, the friction head, and the velocity head. For instance, if the static head is 5 meters, the friction head is 2 meters, and the velocity head is 1 meter, then the total head the pump needs to handle is 8 meters. This formula is covered under UPC 1106.2. Finally, Rule 57 addresses pump redundancy. The thumb rule here is to have at least one standby pump for every duty pump. So, if you have 2 pumps in operation, one should be running constantly as the duty pump, and the other kept as a standby in case the duty pump fails or needs maintenance. This approach ensures reliability and continuous operation. The code associated with this rule is IPC 1106.3. These rules are fundamental in designing efficient and reliable pumping stations, which ties into our overall theme of ensuring effective water management systems. Let's now look at some important maintenance and safety rules to keep in mind. Starting with Rule 58, access for cleaning. A good thumb rule here is to install inspection chambers or manholes every 30 to 50 meters. For example, if you have a 115 pipe, you should place an inspection chamber roughly every 30 meters to ensure easy access for cleaning and inspection. This is supported by the IPC code 710.4, which emphasizes proper access points along the pipeline. Moving on to Rule 59, slope verification. Before you backfill the trench, it's crucial to verify the slope. The best way to do this is by conducting a water test. For instance, a simple drop test can confirm if the slope is approximately 150, which is ideal for proper drainage. This practice aligns with UPC code 710.1 and helps prevent future issues like blockages or improper flow. Finally, Rule 60 focuses on safety clearance. Always ensure there's at least 0.6 meters of clearance above the pipe for inspection purposes. This space allows technicians to work safely and effectively when inspecting or maintaining the pipeline. Together, these rules help ensure the infrastructure operates smoothly and safely, highlighting the importance of proper planning and adherence to standards throughout the project. Thank you so much for being here today. I really appreciate your time and attention throughout this presentation. If you found this information valuable, I encourage you to subscribe for future updates and insights. Staying connected means you'll be the first to learn about new developments, tips, and resources that can help you continue to grow and succeed. Once again, thank you, and I look forward to staying in touch.